definition of velocity. Remember, this is where it all got started. Delta x over delta t. And x here is a position function. Okay, your annoying book puts it as s of t in case calculus BC students are confused between what x? Isn't that x a dependent variable? No, it's not. Is it t? Is it x? I'm going to assume that you're smart enough to know the difference. X is the position, and it's not distance. A lot of people say it's a distance function, but I'm going to explain later. Distance means something else here, okay? It's the position, okay? Let's say on number line, and then your position given as a coordinate as you move, right? Yeah, X is a position function, and if you take a derivative, and of course our notation is this. That is defined to be the velocity, instantaneous slope, if you will, okay? Now, then, of course, what is the derivative of velocity then? One has to wonder, right? And derivative of velocity happens to be, because the other day somebody, and this of course is a second derivative of our position function, eh? Somebody the other day wondered what is the use of second derivative. This is what acceleration is. How about that? Huh? And we all accelerate when we drive, right? Okay. Now in high school physics, acceleration is always constant. So let me briefly talk about what causes acceleration, and of course force, right? It's directly proportional to the force. If I exert greater force on a body, then body will accelerate more. Think football, right? However, if I exert the force on a tiny Asian girl, well, she's going to fly. But if I exert that same amount of force on a 300-pound linebacker, he's not going to move much. It's going to be very slow acceleration. That makes sense to you? So it has to be inversely proportional to the mass. Size of the body matters here a lot. So this is the acceleration, directly proportional to the force and inversely proportional to the mass. Now, assuming mass stays constant, you don't get fat over a few seconds, and we don't approach speed of light. Because if you approach speed of light, then theory of relativity comes into play, and then this increases. So that you don't want that at the moment. So as long as this is constant, then force is just direct variation with acceleration. That's famous Newton's second law equation now, isn't it? Having said that, in high school physics, they always apply just a constant force. The only reason for that is to make your algebra easier. And this thing creates what's called the kinematics equation. Did your physics teacher give you kinematics equation yet? Yeah. Did you see the derivation of that? No, because in algebra-based physics, that takes a whole page. And it's long and complicated process. God, I mean, I've once done it before, don't want to do it again. Today, I'm going to use calculus to show you how concisely this could be done. That's why the language of physics is calculus. You get it? Cannot separate these two. Now, however, those of you who drive, do you really drive with a constant acceleration? Like, who are we kidding? No, of course not, right? I sure don't. So, which means the acceleration is not constant. That means the derivative is not equal to 0, right? So what is the derivative of acceleration then? Right.
It's called jerk.
Jerk. What? What do you mean jerk? What is a jerk? Not the jerk that who dumped you and moved on with your bestie. Not that kind of jerk. Have you been in a stick shift car where the driver does not really know how to drive stick shift? That jerky motion. Yeah, that kind of jerk. Sudden change of acceleration. You get it? And then this thing can go on forever, right? Right. MIT has actually named, there's like 20 somethings derivative, but I mean, in this case, we rarely see this jerk. In high school physics, acceleration is constant, so you only get to see about here, okay? So we'll just call it that. Okay. Then, using this relationship, now we are ready to derive kinematics equation. Let's say our acceleration as a function is constant a, and this is not a smart notation. This is function, and this is constant a. These are not two same a's, okay? But that's what your physics book does. I like to be consistent with it. So we'll just leave it like that. Then think antiderivative. Antiderivative meaning take a derivative of v and you get that constant a. What would be the antiderivative? I'm going to leave a space here, and can you think like that? According to our power rule, this is 1, so you want multiply 1 here, and that becomes 0. You see, it works, right? So, wow, that's our antiderivative, right? Okay, that's nice and swell, except until somebody says, wait a minute, that's the antiderivative as well, because constant I is in differentiation. Wait, so is this. So is this, so is this, so is this. You see, there are infinitely many antiderivatives. No! See, all antiderivative, and when you say antiderivative, they are family of functions. They only differ by constant, so it's a vertical translation, a bunch of it packed together. That's really what antiderivative is. So in calculus, we just write plus c for constant. You get it? Some unknown constant, and we need a little more information to figure out what that c is. However, in physics, we have that information, and that happens to be, well, at the beginning, let's say, this initial speed, it may or may not be 0, right? Let's call it v naught, v original, whatever you want, v0, whatever you want to call it, right? That's the beginning velocity. When you started that stopwatch as a scientist, this particle already might have a velocity, right? And let's try to figure this out. If you substitute 0 here to this t, this dies, and you only have c on the right-hand side, left-hand side will be v naught. So it looks like our c is equal to v naught, eh? And for some reason, instead of putting it here, physics book always puts it there. Okay, those of you in physics class, now this looks a little familiar now, right? Okay, well, we'll take another antiderivative, then this thing becomes position function, like I said. And then you will have another constant. Let's just write the constant down first, or C2 if you will. And this is V naught T. And one might think, yeah, this is the antiderivative, right? Let's check. Power rule puts that thing in the front, right? Whoops, it screws up, right? Because we don't have 2 in front up there. This right here. So we have to adjust for this. So I'm going to put 1/2 AT squared. Aha, and then that exponent 2 is going to cancel half in front. And that really looks familiar now, doesn't it? Almost. Now, initial condition. At the beginning, your position may not be at the origin. So we'll call that x naught. And you see, if you substitute 0, this disappears. You only have c. Left-hand side, it becomes x naught. You get it? So we'll put x naught right there. How about that? That is kinematics equation that your physics teacher gave you. While we are at it, why don't we figure out the vertical motion? See, I'm going to call it sub x. Oh, x sub x. Yeah, I guess that we don't need that. Right? And a sub y. And here's a different assumption. We will assume gravity is the only thing that's acting on this body. Free fall situation. Or you throw something directly in the air, there's no external force, right? And g, of course, is approximately 9.8 meters per second square. In feet, it is 32 feet per second square. Okay, that's just a measurement on this planet. This is on the surface. This happens to be the gravitational constant. Have you seen, before you take physics class, have you seen g before? in middle school science? 9.8? Nah? Okay, so some of you, this is your first time then. Oh boy. Okay. Now, we will take antiderivative, so velocity in y direction as a function of time, and then we'll just do it pretty quickly. Another initial velocity minus gt, because we have seen it on the left-hand side with x, and then another antiderivative, and this will be y initial position plus v naught t minus 1/2 gt squared. How about that? Good? Now, here's a little thing about this gt squared. Actually, I'm gonna explain that on the example. Okay, this is the kinematics equation in horizontal motion and vertical motion. So far with me? Okay. While we are at it, we'll derive the projectile motion. Have you seen projectile motion yet in your physics class? Oh, okay. So some classes pretty far advanced. Projectile motion is if you have if you throw a ball. I have graphics for you. See, this is a projectile motion. This blue arrow is the velocity vector, initial velocity as you launch this projectile. This is a football, best sports series, field goal. So kicker kicks it harder, and it makes it go farther, right? However, launch angle also affects the path of the projectile. This red curve is the path of the projectile, okay? So, I'd like to figure out the governing equations of these two, okay? Now, I'm going to copy this into your notes. Okay, about that much. Okay, now I'm going to put it somewhere there. And of course, it always turns out to be huge. Okay, I'm ready. Could be a little bit bigger. Say it's about that big. Okay. Now, here is different assumption that comes into play. So there's one in blue. Projectile motion. Okay. First, I'm gonna copy this thing down. So your x, remember, was x naught plus v. Instead of naught, I'm going to put little x here too, because we are going to put both x and y in it. And this is x direction squared. And your y here is what we have up there, y naught plus v in y direction, t minus 1/2 gt squared. Okay? Assumption here is the gravity is the only force acting on that projectile. No external force other than launch, which makes this thing is 0. Okay? So G is still there. And the other thing is, see, the launch position may or may not be origin, right? It could be at the top of the building. However, if you set this position to be the launch position, makes your life with algebra-wise so much easier. So in case it's at the top of the building like this, then this ground is like y is equal to negative 10 meters or something, right? Let's do it that way. We can always adjust it because we, the scientists, decide where the origin is. So this is the origin. You get it? Okay. So that's another assumption that goes into this, which makes things a lot more convenient. This is 0 and this is 0. You get it? Now, I like to figure out these little components of velocity now. So this is a velocity vector v originally. Now then, this is a velocity x and this is a velocity y component. Now, if this angle is theta, then as you can see, velocity x component is v cosine theta a. Too much trick? You got this? And velocity y component likewise is then v sine theta a. Okay, well then, let's substitute and simplify these expressions. So x happens to be v cosine theta, And then when you write t, just to emphasize, we don't have to write that parenthesis, but that t is not inside cosine, okay? Cosine t, cosine theta, that's constant. Once you launch the projectile, you lose control over it. It's going to land where it's going to land. You cannot guide it, right? That's how ballistic missiles work. That's why hitting accurate target with a ballistic missile is so tricky, because you have to launch it and send it to the other side of the planet and be accurate about it without any guidance control. Okay, and that's it. And then your y happens to be v sine theta. Once again, this whole thing is constant times t, but it has one more component, gravity component. This is it. This is a projectile motion that your physics teacher gave you already or about to give you. While we are at it, we'll figure out the velocity, x component. Remember, it's a derivative with respect to t, so this is it, constant velocity in x direction, and velocity in y direction happens to be v sine theta minus that 2 comes down and cancels, so gt. Okay, up to whatever I talked about now, other than the definition of what velocity and acceleration is, you don't have to worry about it on tomorrow's quiz. Okay? What I'm about to show you here is a fair game now. Okay, so from now on, it's a really good time to wake up now because this is subject to your quiz. Okay, let's see, right there. You notice that equation is what I had up there? V naught t minus 1/2 gt squared. You see it's in that form. Ah, that's where that thing came from. And 4.9. I told you that g is equal to 9.8, right? So of course, that's 1/2 g is 4.9. You get it? Now, many of you in algebra class, whenever you have a height function, not squiggly, I don't mean squiggly equal to. This could have some kind of initial, but then this was always 16 t squared feet per second squared. You know what I'm saying? In feet. You ever wonder why is it always, this number is, it varies, but the second number is always 16. Why is that always 16? Here is your answer. Remember g is also 32 feet per second squared. Oh yeah, so half of that is 16. So in this planet, it has to be 16. You get it? Of course, some idiot authors put some other number such as 10 instead of 16. Oh, then it's no longer on this planet. They're from another planet. Okay? This kind of tells you how much these mathematicians know about science, right? Okay. So that answers that question. So let's move on. A, find the maximum height of the ball. And this is how you're taught to do this in algebra class. I'm going to throw this picture. See this motion, you launch it upward, and it's not a projectile motion. It goes up and then comes straight down and hits you on the head. Right? However, if you stretch this out into x, this is a y-axis and this is t-axis, then now it's going to look like this. Right? It doesn't mean it's a projectile motion. A lot of teachers at LA try to tie the two together, and I've been telling them, don't, it's going to backfire. They're not the same. They try it anyway, like, why is it not working? And kids laugh at them. Okay, this is t in seconds and y in meters, okay? So not the same thing, as projectile motion. Don't get these two mixed up. And then the maximum axis of symmetry is right there, isn't it? We'll just call that Tmax. But finding that is not enough, because when we say maximum is a y value, isn't it? Maximum is always a value of the function, okay? It's not the x value, or in this case, t value. However, we like to use calculus. Not that I'm not gonna insult you with something this obvious, right? So let's practice with calculus. A, find the maximum height. We already know what that is, but let's use the derivative. Oh yeah, there's a nice definition right there, right? Velocity, I told you, is the derivative of y, right? Now this dy dt, I'm just writing it for explanation purpose. You don't have to give it to me. You just take a derivative. So it's a 30 minus 9.8 t. You got that? Now at the maximum, what do you see? Anything that's going up will slow down eventually, and it has to stop before it comes back down, eh? And if you like to think mathematically, slope right there, the derivative has to be 0, it's flat. So it's like there's that connection between math and physics. So we set this thing to 0. And then I'm pretty sure you can solve that equation, and we'll call this T max. And that is squiggle equal to, why don't I just recycle it from the notes? Does somebody punch the calculator and tell me what that is? Okay, fine, never mind. 3.06224. Don't forget. See, notice that I use a squiggle equal to because I rounded something, and then I put the unit down. Yeah, these two are essential. Don't forget those two. Okay. That is the time that gives you the maximum height. We haven't figured out the maximum height yet. This is not a complete answer. So your maximum is a y value, like I said, and then you plug this thing in, right? Plug it into y, meaning this equation right there. You get it? So if you do that, then it will give you, if you don't screw up button punching, meters. Good. That's part A. Any questions before I move on to part B? Part B, find the acceleration of the ball. Oh, that's easy. Acceleration, of course, is the derivative, right, of velocity, and we have velocity right here. So that's just negative 9.8. That's it, eh? How about that? In meters per second square. That's the gravitational acceleration. Okay, now C. When does the ball hit the ground? Well, that's gotta be here, right? We'll call it T ground, G, T final, whatever. T1, T2, however you want to label. Subscripts are great, so that when we substitute like this, we don't have to really write so many decimals. Okay, so right there, what do you know about that place right there, this point?
Mr. Kim?
Yes.
I would think that 2 times t, the ball is maximum height.
Yeah, that happens to be the case in algebra 1 type of easy insulting problem like this. But if it's a little more complicated case, then what do you know? It's not necessarily double. I would never put something this easy on the test. I'm kidding, no, right? You're gonna have to use calculus to do it. I'm just using this algebra example to teach you the method of doing this, like procedure. You get it? You notice that your y has to be 0 because it's on the ground. Right. So, we have our y up there. That one, right? Okay. Can I factor t out? So t and then 30 minus 4.9 t and set that to 0 like that then. And that t, which we get, well, one of them is 0. Oh, that's exactly 0. That represents this point right there, which is not the point we're looking for. Or the other t happens to be, and if you punch the buttons correctly, it'll be 6.1224449 seconds, which is exactly double of what we found up there. Okay? Now, this is what we call T ground. Now we want, what do we want? Velocity, right? Some people actually like, what? Which one do I substitute where? Shall we plug it in here? mean, shall we plug it in here? Guess what you're gonna get if you plug it in here? You get 0. That's how we got this point, right? We have to plug it in here because we want the final velocity. You get it? So our velocity at t ground is equal to, and this is a shocking number. What? Exactly -30. Are you surprised by this? No, of course not. Didn't your physics teacher teach you that if you fire a gun vertically upward, what goes up must come down, and when it comes down, it's same velocity as firing a gun at somebody's head? Yeah. Actually, that's not true. Air resistance. It's only true if it's done in vacuum. Not true. So if you do that experiment in surface of the moon, yes, it's true. But Earth's atmosphere, oh, air resistance is quite a bit. See, the bullet, they call it muzzle velocity. When it comes out of the barrel, it's supersonic. That's what gives you that pop sound. When it comes down, there's no way it'll accelerate to supersonic. The air resistance is just too big. It reaches to what's called the terminal velocity. Chapter 6 will calculate that too. So not even close. But this is assuming in high school physics, there's no air resistance. So it's exactly the same. You notice that negative sign? Should we remove the negative sign and just say 30? No, you don't. It's a velocity. It could be negative. It's a vector. It means it's downward. Okay? So don't be getting rid of those negative signs. Any question? Yeah.
Yeah, Mr. Kim.
Yes.
So on the quiz, if we don't get a calculator, do we just put like 30 over or 300 over 49 for T?
Yeah. Yeah, something like that. Numbers will be nice tomorrow because it's a non-calculator quiz. Okay. I'm kind of combining this with your physics class. And in physics, of course, after that, you figure out the number of sig figs, right? Okay. Any other question before we go to the next example? Okay, here's the next example. Now, oh, you see that cubic function? So your acceleration may not be constant, which means this kinematics motion that we just figured out does not apply anymore. So you have to know what you're doing, but calculus will always work. Okay, so that's our position function. Now, velocity at time t, oh, that's easy, warm-up round. Velocity, of course, is the derivative of that thingy. So we have 3t squared minus 12t plus 9. Good. Say yes. Okay, that's easy. B. What is the velocity at 2 seconds? Somebody punch this into the calculator and tell me. And somebody else punch this into the calculator and tell me. Okay. First one is how much?
-3.
-3. And what do we put after -3?
Meters per second.
Of course, right? Okay. Well, and the second one, somebody else?
9.
9. Okay. I mean, it'll be something like this tomorrow's quiz. Okay. Numbers are nice. Okay. Then C. When is the particle at rest? What do you mean at rest? It's not like a particle needs a rest. So that rest means something else other than you need a rest. I always need a rest, right? But no, particle does not need a rest. What does it mean? Particles at rest.
0 velocity.
0 velocity. There's no motion. You get it? That's what that means. So let's not confuse those terms up. So meaning, this is what that means. You get it? Okay, I'm pretty sure you can handle this algebra. Would it be too much algebra if I factor 3 like that and then factor the rest of the expression like this? Too much algebra? Nah, you got this? Okay, so here we get t is equal to 1 second or t is equal to 3 seconds, A. Okay, that's when the particle is at rest. Can you imagine this? That means the particle is moving this way and comes to a stop after 1 second. Okay, if you cannot imagine this, then let's do D. When is the particle moving in positive or negative direction? Meaning, let's say right side is a positive number line, it's traveling along the number line. What does that mean? And negative direction.
That's positive.
Go ahead.
This positive means the slope will be positive, which the derivative will be positive.
Yes.
And negative is other way.
Yeah, this is exactly what that means. Okay. So when velocity is positive, we say this. If you define this as a positive direction, the right-hand side. You guys see my fingers, right? That's positive, meaning moving forward, and let's say that's backward. You get it? Forward, backward. So, Miss Slattery taught you how to figure out all these inequalities, right? Let's say this is a velocity versus time graph, and this is 1 and 3, and this is positive, negative, and positive like that, right? Right, and in case you're wondering why she's torturing you with all this inequality that you hate, because equations are so much better, this is precisely why. Okay, that class was truly pre-calculus now, wasn't it? So your answer should be here as, instead of infinity, remember this function only exists between 0 and 4 seconds, right? So we don't know what this particle does outside of those intervals. So 0 to 1, union, and then 3 to 4 bracket. How about that? And negative direction, this is between 0 to 3. Oh, I almost forgot. You have to write the units down for these things too. Even in interval notation, you need units. Good. Now, D, draw the diagram to represent the motion. Now do you see forward for 1 second, stops, comes back, and then goes back somewhere? Let's figure that out. So E at t is equal to 0, and then you plug in 1. If you plug in 1 to this original equation right there, what do you get? Somebody tell me. Oh, come on, tell me. We are running out of time. 4. So this is 4 meters traveling to the positive direction. You get it? This is when t is equal to 1. And then somebody plug in 3. But yeah, feel free to use calculator, although you should need a calculator. You get 0. You back up by 4 meters. You get it? Okay, somebody, last chance, plug in 4. Here's a hint. You get 4 back. So motion is boom, boom. You get it? Okay, now I have a question. F. What's the total distance? It's obviously 12 meters now, isn't it? So far, so good. Now here's another question. What is the displacement? And those two are two different things. Physics people.
4 meters.
4 meters, of course.
Well, actually,
this is exactly what displacement means. X2 minus X1. Remember that delta X? Yeah. And that's 4. If you want to be more complicated, you would do that, but you know what I mean, right? It's just how far that has been displaced. This is displacement. How about that? We good? That's why we don't call x as the distance function, because distance means something else here, right? It's a position function. It's a location of that. It's a coordinate. And of course, student of mathematics, we have a better, this is a nice diagram, this thingy and all, but we have a better way to represent this. And that better way is, I was going for the drama. Graph, of course, right? This is position versus time graph. Do you see this thing is moving forward for the first 1 second and then coming back for next 2 seconds and going back forward again? And this is your displacement right here. How about that? You see the power of graph? It just describes everything, including velocity. The slope is 0 right there and right here.